dear students, welcome back to Verilog lecture series. I want you to imagine something. You are in an exam hall, the teacher says start writing, but nobody listens. Some students start immediately, some start after 2 minutes, and some starts after 10 minutes. Some randomly switch papers in the middle. What would happen? Chaos, total chaos. Now here is the crazy part. If digital hardware behaved like that, modern computer would not exist. Not CPU, not GPUs, not smartphones, not even calculators. Today, you will discover the invisible signal that keeps billions of transistors working together. And once you understand this, you will never look at the processor the same way again. In the previous lecture, we learned something amazing hardware can remember. Through latches, flip-flops, registers, memory exists, problem solved. Right? Not even close because memory creates a new problem, a much bigger one. Let's say we have one flip-flop. Easy. Now let's say we have 1 million flip-flops. Who decides when they update? Who tells them update now? And who tells them wait? Because if every memory element updates whenever it wants, everything breaks. So the problem arises, synchronization problem. Imagine this. Flip-flop A updates now, flip-flop B updates 1 nanosecond later, flip-flop C updates randomly. Flip-flop D updates whenever it feels like it. Sounds ridiculous. But that's exactly what happens if there is no synchronization. Hardware becomes unpredictable. And engineers hate unpredictable things. Let's do a small experiment. Imagine a row of dominoes. You push the first one. Does the last domino fall instantly? No. The effect travels. One domino, then another. This takes time. And digital circuits behave the same way. Signal need time to travel. Do remember, dear children, that signal needs time to travel. This is one of the most important truths in engineering. Nothing is instant. Not wires, not gates, not processor. Everything takes time, even if it's only nanosecond. And if memory updates before signals settle, you store garbage, not data. So do remember, signal need time to travel. Nothing in hardware is instant. Imagine a busy traffic junction. No traffic lights, no rules, cars moving everywhere. Chaos. Now add traffic signals. Suddenly order, predictability, safety. That's exactly what a clock does. A clock is a traffic signal of digital hardware. Meet the most important signal in digital electronics, the clock. This tiny signal coordinates billion of transistors. Think about that, billion, all listening to one signal. That's insane. Many beginners think clocks are complicated. They are not. A clock is simply high, low, high, low. You can see a repeating waveform. Low, then high, then low, then high, low, high. This is a clock. Clock looks simple, changes everything. Think about your heart. Every beat synchronizes your body. Now imagine your heart beating randomly. Sometimes fast, sometimes slow, sometimes stopping completely. Disaster. The clock is the heartbeat of a hardware. Do remember, dear students, clock is the heartbeat of hardware. Imagine an orchestra without a conductor. The drummer starts early, the Guitarists start late, the violinist start tomorrow. Terrible. Now add a conductor. Everything becomes synchronized in hardware. Clock is the conductor. There is where things become mind blowing. One clock signal, millions of circuits, billion of transistors, all following the same rhythm, the same timing, the same schedule. That is synchronization. So, this is the golden or global rhythm, billion of transistors synchronized through one clock. But wait, here is the weird part. Most circuits don't care about the entire clock. They care about a moment, a tiny moment, a microscopic instant in time. Clock edges matter. So let's see positive edge. Look carefully when the clock changes from 0 to 1. 0 to 1. This is 0, this is 1. This is the positive edge. That moment is called positive edge or rising edge. So this particular edge is positive edge or it is rising edge. What is the system update exactly here? Not before, not after, right here. There is another edge, negative edge, negedge. It transition goes from 1 to 0. This is called negative edge or falling edge. You can see high, then when we are going to lower part, this is the falling edge or we can call negative edge. Some circuit use this instead, but the idea is the same. Update only at a specific moment. Great question. Why not update continuously? Wouldn't that be faster? Actually, it would be chaos. Signals would constantly changes, memory would constantly change, nothing would stabilize. Hardware needs discipline the clock provides. So we should maintain order and stability. Think, then update the real purpose of clock. This is the most important idea in today's video. Hardware follows a simple strategy. Think, then update. Think, then update. Think, then update. The clock is hardware think time to think and then tells it exactly when to act. Now connects the dots. Memory stores information, clock controls timing. Together they create a reliable system. Dear students, remember this. Memory stores information, clock controls timing. Together they create reliable system, reliable computing. Without memory, nothing is remembered. Without clocks, nothing is coordinated. Now again, you have probably seen this before also. Always at the rate posedge clock. Maybe it looked scary, maybe it looked confusing. But now you understand something important. The line is simply saying do something when the clock rises. Positive edge means rising edge. So that's it. Suddenly Verilog starts making sense. What happens on every tick? Think of every cycle as an opportunity. Tick 1, capture data. Tick 2, capture data. Tick 3, capture data. Tick 4, update memory. Tick 5, move to next state. Next tick, perform computation. And this continues billion of times every second. So every tick, capture and update. The gigahertz mystery. Now let's solve another mystery. Have you seen CPU advertisement? 3 gigahertz, 4 gigahertz, 5 gigahertz? What does that actually mean? 1 gigahertz equals to 1 billion cycles per second. Let that sink in. A 5 gigahertz microprocessor receives 5 billion synchronization events per second. That's why modern processors are so powerful. Now you might think, why not build a 100 gigahertz processor? Sounds amazing, right? Not so fast. As cloud speed increases, heat increases, power increases, timing problem increases, engineering becomes harder. That's why clock design is one of the hardest job in semiconductor companies. So think about this. Higher the frequency, higher will be the heat, higher will be the power, and higher will be the timing problems. So trade-off exists between the frequency and these three parameters. That's why clock design is one of the hardest job. Look at this. If you want to become an FPGA engineer, field programmable gate array, remember this. Everything revolves around clocks, counters, state machines, UART, memory controllers, processors, everything. The clock is everywhere. So what is a clock? Not memory, not computation, not storage. A clock is synchronization. That's its purpose. And it's one of the greatest invention in digital electronics. Write this down. Seriously, write it down. Memory stores data. Clock controls when it changes. Memory stores data. Clock controls when it changes. Without memory, no computing, no CPUs, no RAM, no smartphones, nothing. Without clocks, no coordination, no synchronization, no reliable system, nothing works together. Look at our journey so far. Why HDL exists? This code becomes hardware. How hardware thinks, how hardware remembers, why clock exists. Everything connects. Nothing was random. Every video prepared you for this moment. So, till now we have seen combination logic, sequential logic, flip-flops, registers, clock, FPGA, CPU. Now look at this. We understand the clock. Always at the rate posedge clock. Begin, then question mark, then and. But what exactly happens inside? What is an always block? Why does every Verilog design use it? And why is it one of the most important constructs in RTL design? In the next video, understanding always block. You will learn what is an always block, why does RTL depend on it, combination versus sequential always block, how real FPGA designs are written, and that's where we stop talking about hardware and start designing it. If you are following the RGPB HDL syllabus or want to become an FPGA RTL engineer, subscribe and continue the journey. RGPP HDL playlist ED302 Introduction to HDL. We will continue this in the next video. Thank you. See you in the next time. If you like this video, give thumbs up and share this video with your friends and subscribe to the channel. This will support me. Your support means a lot to me. You are now one step closer to becoming an RTL and FPGA designer. Thanks for watching. See you in the next lecture.